Good evening, everyone. Welcome to Clean Energy Seminar, a ReHyCaRe student event organized by Sierra Group, Department of Chemical Engineering, BUET, in collaboration of all the ReHyCaRe partners. I am Samira Hossain. I am a research associate of ReHyCaRe, and I'm also your host for this evening. For those of you curious about what ReHyCaRe actually stands for, ReHyCaRe stands for Renewable Hydrogen Generation with Carbon Recycling from Biogenic Residues of Bangladesh. It's a clean energy project under peer program funded by USAID and implemented by National Academy of Sciences, Engineering and Medicine. The ReHyCaRe Consortium brings together three leading universities of Bangladesh: Bangladesh University of Engineering and Technology, Bangladesh Agricultural University, and University of Dhaka, along with our USD partner, Florida Institute of Technology. You can find more about our project and the upcoming events in our project website, ReHyCaRe.com. So this Clean Energy Seminar is a periodic event arranged by all the partner institutions of ReHyCaRe. So the main goal or the aspect of this event is to disseminate the knowledge about the current research that is going on in the clean energy or low carbon technology. And we also want to demystify the field of clean energy by sharing the exciting research. And as you can all see that this is a student event. So this event is especially catered towards the current undergraduate and graduate students in science and engineering to share about the insights from experts and current researchers in this field, and also give advices or insights about career aspects in clean energy. So today's event is a reflection of all our goals and motto. So our event today is focused on a very interesting topic currently in clean energy, that is hydrothermal carbonization of lignocellulosic waste for bioenergy. It is my pleasure to introduce you to our speaker, Mr. Tahmid Islam. Tahmid Islam is a third-year PhD student in Department of Chemical Engineering at Florida Institute of Technology. His research focus is in mild hydrothermal pre-processing for upgrading biomass. So he has already published 3 peer-reviewed journals and presented in 8 local and international conferences. He has also won the 2021 Outstanding Graduate Student Presenter at Florida Academy of Sciences. So our speaking session will be followed by a discussion session. And I'm very excited to announce that we will be joined by Dr. Nipu Saha. Dr. Nipu Saha is a postdoctoral research associate at Idaho National Laboratory at USA. He has an extensive research career and focus on biomass conversion, thermochemical conversion of biomass to energy and material. And he has also published 19 peer-reviewed journals and delivered over 22 conference presentations on thermochemical conversions. So our speaking session and the discussion session will be moderated by Shupriyo Kamal from Sierra Group of BUET. But before we go into the next part, I would like to invite Mr. Anthony Mukim from USA to share some words towards the participants.
Thank you, Samira. Good evening and good morning to you. I am Anthony Mukim and I work in the energy team of USAID Bangladesh, and I am the USAID activity manager of this ReHyCaRe project. Thank you for joining this first student seminar on hydrothermal carbonization of lignocellulosic waste for bioenergy. I'm glad to be able to attend this virtual learning event today, and I am joined today with my USAID colleague, Mr. Shahan Shafi, our senior energy advisor. For more than 2 decades, we have been helping Bangladesh transform its energy sector. USAID has also championed clean energy innovation by assisting academicians, the policymakers, the private investors to identify and reduce the technical barriers and investment risks, promote public-private partnerships and tools and resources to develop renewable energy projects. Today's Clean Energy Seminar is one of the glowing examples of our efforts. This is an event for the undergrad students who aspire to excel in research and innovation. Partnerships for Enhanced Engagement in Research, we call it PEER, is a program of USAID that provides grants to local research organizations and academic institutions to conduct research on myriads of topics in line with the USAID Bangladesh development strategies like health, the education, the agriculture, women and gender, etc. The Renewable Hydrogen Generation with Carbon Recycling ReHyCaRe project is a research grant under the PEER program of USAID, which was awarded to the BUET, DU, the BAU, and also the FIT. Through this project, the 4 academic institutions will conduct research on generating renewable hydrogen from the biogenic residues. And in addition to that, USAID Bangladesh has a MOU with the Research Innovation Center for Science and Engineering, the Rice Department of BUET, to collaboratively work to promote renewable energy in Bangladesh under the Reinforcing Advanced Energy System, we call it RISE program. And also USAID Bangladesh promotes institutional partnership, youth engagement, research, and innovation opportunities in the energy sector of Bangladesh through the other 2 projects, and those projects are Bangladesh Advancing Development and Growth through Energy, we call it BAT, and also the Bangladesh Energy Regulatory Partnership Project. The energy transition of Bangladesh requires research, innovation, and collaborations from the academicians, particularly young students like you. The future of the clean energy sector relies on you. It is very encouraging to see that you have started acting on it right now. Today's seminar has opened the door for you to learn more on clean energy sector, and I welcome you all to this event and look forward to your active participation in it. Thank you and all the best.
Thank you, Mr. Mukim, and good evening, everyone. I'm Shupriyo Kamal, currently an assistant research engineer at Seer Group, and today I'll be your moderator for the talk and discussion section. Samira has already introduced us to our esteemed speaker and discussant, and now I'll take a few moments to outline today's talk and discussion. The talk will focus on the technology of hydrothermal carbonization, and after that, we will have a discussion section with Dr. Nipu Shaha and Mr. Tahmid Islam. During the discussion, we will talk about a few technical aspects of hydrothermal carbonization and then move into the broader aspect of clean energy research. We will also hear about Dr. Nipu Shaha and Tahmid Islam's personal experiences in their research career and also take relevant pieces of advice. I highly encourage the participants to drop their questions in the chat box at any point during this webinar, and we'll pick up a few of these questions during the Q&A session. I hope you're as excited as I am to hear from our esteemed speaker, Mr. Tahmid Islam, and our very special guest, Dr. Nipu Shaha, who are engaged in state-of-the-art research in biomass conversion using clean energy technologies. And without further ado, I would humbly request Mr. Tahmid Islam to present his talk.
Thank you, Shupriyo. Good morning. Can everyone see my screen?
It's visible. Please go on.
Good morning, everyone. I'm Tahmid Islam, a PhD student in the Department of Chemical Engineering at Florida Institute of Technology. Today, I'm going to present on hydrothermal carbonization of lignocellulosic waste for bioenergy. First of all, let me introduce my research interest, which is classified into 4 different sections. Biomass, which focuses on air classification of biomass, hydrothermal carbonization of air classified biomass, and integration of air classification and hydrothermal carbonization. Deep eutectic solvent. This focuses on biomass softening by deep eutectic solvent, de-ashing of biomass, and recyclability and quality assessment of DES. Plastic. This focuses on mainly the co-hydrothermal carbonization of biomass and plastic blend, and mass and energy density of hydrochars. water. This focuses on hydrothermal carbonization derived process liquid recirculation effect on surface functionality and absorption of cationic dye from water. Today I am going to focus on hydrothermal carbonization part only. So water is a magic solvent. Water can be classified into two different types, subcritical water and supercritical water. As you can see in this figure, this is a three-phase diagram of water, where in the y-axis we have water vapor pressure, and in the x-axis we have water temperature. So if we increase the temperature of water, we can find a triple point where water can coexist as solid, liquid, and vapor. If we further increase the temperature in between 100 to 374 degrees Celsius, water acts as a subcritical water, and above the critical point, water acts as a supercritical water. So subcritical water has some unique characteristics that makes it valuable for hydrothermal carbonization. For a subcritical water, the solvating power is very high. The viscosity and surface tension of the water is low. The diffusivity is very high. The polarity is very low, and the self-ionization is also very high. As you can see in this figure on your right-hand side of the screen, in the y-axis we have the water density, and in the x-axis we have the temperature. In the primary y-axis, secondary y-axis, we have dielectric constant of water and water dissociation constant. This is the physical properties of water with temperature at 24 megapascal. As you can see, if we increase the water temperature, the dielectric constant decreases, the density of the water decreases, but the dissociation constant increases. We all know that water can be dissociated into hydronium ion and hydroxyl ion. So when the water dissociation constant increases, basically we also increase the hydronium ion as well. That makes the water acidic in subcritical zone. And also when the dielectric constant decreases, water acts as a nonpolar solvent and an ionic product. What is really a lignocellulosic biomass? Lignocellulosic biomass is a plant dry matter. It is the most abundantly available raw material. It can be found in a macrofibril, which is located in plant cell of plants. It has 5 different key elements, which are hemicellulose, cellulose, lignin, extractives, and inorganics. Except the lignin, hemicellulose, cellulose, extractives, and inorganics are encapsulated in lignin structure, and combining them, we call them lignin carbohydrate complex. So what is really a hydrothermal treatment? When we have a water, in the room temperature, it remains as a liquid. When we increase the temperature, we also increase the water vapor pressure as well. If we have a closed system where we have water and we are increasing the temperature of the closed system, we are increasing the vapor pressure, and therefore between around 160 degrees Celsius to 280 degrees Celsius, water acts as a subcritical zone, subcritical water, and causes a carbonization reaction if the water reacts with any kind of solid in the high pressure, high temperature system. If we further increase the water,
I'm sorry, Mr. Tahmid Islam. I think there is a communication error from your end. So it might take a little bit of time for Mr. Tahmid Islam to join, but meanwhile, since we have our esteemed guest, Dr. Nipu Shaha, so let's move forward with one of the discussion topics. So to Dr. Nipu Shaha, so when we typically talk about clean energy technologies, so our primary stereotypical idea is mostly about biogas, solar panels, or wind farms, which are very important renewable technologies. But the thing is, the clean energy research sector is more than that. So things like designing advanced catalysts or functional polymers, synthesizing green solvents, and more of these. So can you elaborate on some of the diversity that the clean energy research avenue holds for us?
Thank you, Shubhio, for giving me the floor. Yes, so even when I started my research on clean energy, I knew like, okay, I have to produce the energy like fuel. So my my first term as clean energy was like, as I said, like fuel. But over the time, like when I get introduced with that research, I saw like the diversity is like it has like so many diversities. So you can do so many things from there, not only the fuel. So from my research area, you can see like I work with a material, which is one of the growing field at this moment from the waste or biomass feedstock. So as you already mentioned, some of the thing like functional polymer development. So if you can develop this material, you can use that material in different purposes. For example, you can use those material as battery. So you can like move into the battery research. You can do supercapacitor. You can make the fuel cell. So you can move into that fuel cell research. And you already mentioned one of the topic as well, like the adsorption. So you can move into the adsorption research as well. And not only those, the item I mentioned, you can also use in the medical science as well. So people are using those material for drug delivery. So you can conduct your research on that side as well. So like that field is growing. So one of the thing as this presentation is like you guys are doing the hydrogen production from the west. So this is one of another growing field at this moment. So people are talking about the clean energy. So they want actually zero emission. Like no one wants to throw carbon to the environment. So that field is growing. So you can do several things from here.
Absolutely. And to add to it a bit more, for example, there are extensive research going on developing advanced catalysts for carbon dioxide to fuel, so which inevitably might be a very important aspect of the clean energy industry. And if I share with you one particular kind of polymers, so they're developing a very hydrophobic polymer to be used in coating on ships. So what it does, it reduces the drag of the ship, and the ship in turn needs lesser fuel to go a certain distance. So it increases the mileage. So I think working on other aspects that involves polymer chemistry and other things, you can also call yourself being involved in the clean energy sector. So it's not necessarily the very obvious things like solar panels and biogas, which are very important, but
exactly.
Exactly. So please go on.
Yeah, I would like to add one more thing. As you said, like that hydrophobicity, and Hamid already mentioned one of the things that hydrogen is hydrophobic. So one of the challenge even in the food in energy industry, like fuel industry. So when we produce that energy, like biomass has energy content itself, but the problem is to store or transport those biomass because they are bulk. They are kind of hydrophilic, so they can add water. So over the time, it will like lose its energy values. So the product Tahami is producing, the hydrogen, they are hydrophobic, so it can like stay good for longer time compared to biomass. So this is one of the field as well.
Absolutely. And I think one of the advantages that hydrophobicity of biochars is that when you have a hydrophobic solvent, it contains less water, so you're actually transporting the fuel and not the water. So if from a techno-economic point of view, it's also useful for us. And as someone who has worked extensively using hydrothermal technology to synthesize advanced materials like carbon quantum dots, various adsorbents, and even electricity storage materials. So This seems like a new avenue of research that is exclusive, not only exclusive to hydrothermal carbonization, but what do you think the challenges are right now in developing these materials using hydrothermal carbonization technology?
I would say like throughout my research and up until today, the biggest challenge is the feedstock variability. So the feedstock we are actually working with mostly biomass or the waste material. It's coming from different sources. So when you are taking waste, they are kind of heterogeneous. So when you are making some product from those waste or even biomass, like if you take one part of the biomass and someone take another part of the biomass, like I'm talking about like for example a pine tree. If you take the part of the pine tree or someone take the stem of the pine tree, they will be different. So if you treat those feedstock and produce a product, there might be a high possibility like you and me like working with this, like you can say, okay, I'm working with municipal waste. I can say, okay, I'm working with municipal waste as well, but our product might be different because although they call municipal waste, their internal quality, they are different. So this is one of the biggest challenges, I would say. I'm lucky that I'm working on those. I'm trying to solve those problems at this moment. So that is one of the problem. And another problem is like, I would say, when I did the research, as you said, like I work with quantum dot, I work with energy storage material. The problem I would say for example, the energy storage material, the material I found, I tested it, okay, it can store energy, but I don't know like how long it can store. If you want to store energy, definitely you want to reuse that material. You don't want to use it just for one time. So I didn't check like how the recyclability, like how many times I can recharge, and how that will like how long that material can sustain. So it is still in the initial phase. So there are so many things you can do in later, like in terms of research phase. So these are the difficulties, I would say. We have to think. One more thing I want to add, like when we are doing research, like for the new technologies, mainly we focus on the product. But when you develop that product, one of the biggest challenges is to make that process feasible, like economically feasible. Otherwise, no one will take that process. So in that phase, like you have to think. Sometimes, like when you are making cool product, that process might be very expensive. So you have to think like, how can we like reuse the byproducts? Byproducts I'm talking about, sometimes you can make waste like from your process. So you have to think about like, how can I either reuse that waste, or like how can we treat that waste in a like better way to make the process viable. So this is one of the challenge as well for new technologies.
So absolutely, I think in the research phase where we are developing so much technologies, like there are graphenes and various sophisticated materials, but we don't see their applications in our day-to-day lives. So one of those reasons being is that the material ends up being so expensive. So everybody's focusing on the material itself, but not focusing on the process development, right? We need to have a cheaper, inexpensive process. And from that matter, yeah, from that perspective, do you think that HTC would be a cheaper process? It's definitely producing bioenergy as its main product. Can we use that bioenergy in turn to sustain the whole process? So I would like to hear your opinion on this.
Like when you are making those material or other products, HTC is not only the treatment. So you might need to add some other post-treatment as well to make this product. So if you consider like the whole process, like not only HTC including other post processes, then my opinion is like sustain the whole process might be questionable, but only the HTC process, like sustain only the HTC process, I would say is possible. Like it can sustain from the bioenergies getting from the HTC, it can sustain, the HTC process can sustain from that product for sure.
Absolutely. So that's
just one thing, like if I miss something, I think Dr. Reza is there. You can definitely add something.
So since we have Dr. Tawfiq Reza with us, so I would like to request him to share some of a few opinions if he can come in. Definitely, we would appreciate that.
Oh well, I was gonna write something, but you guys have discussed many of the topics. So I guess one of the things is when we are thinking about bioenergy, we almost certainly think about bioenergy production, but it's not the energy itself. So the energy requires production. It also requires the storage, transportation, utilization. Okay, so if you think about that, so Shupio, you mentioned about the solar wind. So can biomass play a role of that? So this is a big question. Like, okay, can we actually have the biomass derived product to store bioenergy from wind? So this is not like what I want to say is we are not in competition. We have to be adaptive to whatever resource available to us. So this is something that we probably need to do. Well, HTC is one of the processes when if we have a lot of wet biomass, we can produce it. But at the same time, we need to think about how are we going to utilize it. Do we have enough a boiler that would actually take the hydrochar and produce energy? Are we going to make emission, and how do we actually reduce the emission to it? So I mean, those are still some of the important questions that we need to do. And of course, Nipu is right, and also Shuprio, you're right as well. I mean, when we think about the product, everybody is thinking about, okay, so I'm making a cool carbon, I'm making graphene, I'm making carbon quantum dot. Let's make it. But as a chemical engineers, we need to think about the process. This is where we shine. Can we make it effectively? What is the kinetics to it? How much it would cost? Where we can use it? How do we do the life cycle assessment? Because we have to dispose it. So I think ahead. So I was gonna say, I think instead of answering a bunch of answering some, I might have actually open the can of worms. So
yeah,
those are something. I mean, you guys are. We have to answer those questions. And this is as early as we can start thinking about it. We would actually be able to come up with a solution. And in this case, there will be multiple solutions. It is absolutely possible.
Absolutely. And what you say about integrating different processes is very important, because from a holistic view, you can just compete, you can just put two technologies into competition. If one technology provides a better way of storing energy, then couple it with something that has a low plant factor, like a low supply. So you couple it with a better storage technology and integrate it to make a very feasible, financially feasible process. So that's something I think the chemical engineers are very good to analyze. And something like techno-economics might seem like techno-economic studies seem very unattractive compared to developing very advanced materials. But I think at this point, we all agree that we all have too much advanced materials on our hands, but we don't know how to use those materials in our daily life. So that's a really big problem. And I can see Mr. Tahamid Islam is back with us now. So I would request Mr. Tahamid Islam to continue from his lecture. And thank you for being so patient with us. So these things happen in online webinars, and good thing it's an online webinar and we can pass the time talking to various people. So that's all from me.
Sorry, I had a network issue. That's why I had to log into my phone, and I'm going to share my screen from the computer. I'm really sorry about that.
Absolutely, it's all right. So please go on.
Can you see my screen now?
I can see your screen, so hopefully a lot of people. So if someone,
Yeah, you can see it. Yeah.
Okay, so this is where I was. When we have our, so I have talked about the water, which is a very magic solvent, and water can act as a subcritical water in the hydrothermal carbonization zone. So let's first see what is really an hydrothermal carbonization treatment or hydrothermal treatment. So when we have water and we increase the temperature of water in a very closed system, in between 180 to 280 degrees Celsius, water reacts with a solid. If we let them react in a high pressure system, it occurs carbonization. And in fact, above 280 degrees Celsius, water acts as the subcritical water as well, and it occurs hydrothermal liquefaction. So in this zone, from 180 to around 350 degrees Celsius, water acts as a subcritical water and occurs two different types of reactions: carbonization reaction and liquefaction reaction. And as soon as it reaches the critical point, which is around 374 degrees Celsius, above this critical point, water reacts with the solid and occurs catalytic gasification and high temperature gasification. So our main focus is on carbonization reaction in this presentation. And on your right hand side of the screen, you can see the phase diagram as well. Here we have our water reaction with solid. In the carbonization zone, there are numerous reactions happen at the same time. For example, some notable reactions are dehydration or hydrolysis reaction, hydrogenation, hydrogenolysis reaction, aqueous phase reforming, aldol condensation reaction, isomerization reaction, and oxidation. So what is really a hydrothermal carbonization reaction? Hydrothermal carbonization reaction is when we have a high pressure, high temperature reactor, we feed the reactor with biomass and water, and we set the temperature between 180 to 280 degrees Celsius. We set that residence time, it depends on us. We can set it from 1 minute to 12 hours or more. We can have our hydrothermal reaction occur in this high pressure, high temperature reactor. Since this is an autogenous reaction system, the pressure varies, the vapor pressure varies from 1 megapascal to 5 megapascal. And after the HTC reaction, we get three different types of products, which is gas, mainly the carbon dioxide, energy dense hydrocarbon, and processed liquid. Since regardless of the feedstock, it could be agricultural residue, it could be forest residue, it could be organic waste, it could be animal manure, we can have our hydrothermal carbonization done in a high pressure, high temperature reactor system controlling four different independent variables, which is temperature, reaction time, catalyst, and pressure. And after the hydrothermal carbonization, we can get our hydrochar. And hydrochar can be used in versatile applications. For example, carbon material, low cost adsorbent, solid fuel, soil amendment, catalyst, and fuel cell efficiency material. Now, since there are multiple reactions occur in hydrothermal carbonization, some notable reactions are hydrolysis, dehydration reaction, decarboxylation reaction, polymerization reaction, condensation reaction, and aromatization reaction. So after any kind of HTC reaction, our first and foremost work is to find out the mass yield, how much mass we are getting out of the HTC reactor. So when we feed our reactor with biomass, we get the solid char. Since the solid is reacting with water, the amount of solid we feed to the reactor is not the amount we get in the hydrochar. Therefore, because the solid is reacting with water and forming gas, liquid, and solid, therefore some part of the solid is going in the liquid and gas form, and therefore we are getting a low amount of solid compared to our feed amount. As you can see in this figure, if we have mass yield in the y-axis and temperature and time in the x-axis, we can see at the very beginning, all of the reactions happen with 100% of feed, but with time, we are seeing low mass yield. That means that our solid is degrading into multiple products. In some part of the solid is going to the liquid, some part of the solid is going to the solid. As you can see in this figure, this is our HTC reaction at 200 degrees Celsius. And if we increase the HTC temperature, we are getting even low mass yield. This tells us that if we have low temperature HTC reaction, we will have higher solid content and lower processed liquid or gas. But if we have high temperature HTC reaction, we will have higher processed liquid or gas and lower solid content. This justifies that. When we do the HTC reaction, the hydrolysis reaction is more prominent for low temperature HTC reaction. Therefore, we get higher mass yield. And at high temperature HTC reaction, we get low mass yield and high processed liquid. That means the dehydration reaction is more prominent. And our model prediction also tells us how the mass yield is best suited for the experimental values as well. So what is really a hydrochar? Hydrochar is an amorphous carbon sphere size ranging from 100 nanometer to 10 micrometer. It has a very low BT surface area, less than 50 meter square per gram. If we look at the literatures for activated carbon or high temperature biochars, they have around 200 to 500 meters square per gram. Compared to that, it has very low BT surface area. It has a hydrophobic core and high oxygen functional groups on the surface of the hydrochar. It has energy content in between 20 to 28 megajoule per kg, and it has its excellent absorption capacity of heavy metals and organic contaminants. So in this slide, you can see this is a raw biomass pellet where as soon as we dropped a liquid droplet, basically the water, it soaks the water, which shows us that how hydrophilic our raw biomass pellet is. But in this case, if you see, this is a hydrochar pellet, and as soon as it touches the water, it does not soak the water like the raw biomass pellet. If you look at the scanning electron microscopy image, you can see before the moisture uptake, there are some cracks and voids in the raw biomass pellet, but after the moisture uptake, the number of cracks and voids increases in the raw biomass pellet. But for the case of hydrochar pellet, you can see this is already very compact and tight before the moisture uptake. But after the moisture uptake, you can see there are less number of cracks compared to our raw biomass, which proves that hydrophobic hydrochar pellets are mainly hydrophobic, and we can increase the hydrophobicity of our sample. So what is energy content? Energy content is basically the amount of energy present in a sample. And what is energy yield? Energy yield is how much energy can we get from our raw biomass sample. As you can see, when we in the y-axis we have our higher heating value, and in the x-axis we have our energy yield. So when we have our raw biomass and we convert it into hydrochar, we can see there is an increasing trend in the higher heating value. That means we are getting more energy in our sample with hydrothermal carbonization. And also the energy yield is around like 65% to 80%, which means that after the hydrothermal carbonization reaction, we can get approximately 65 to up to 80% of energy from our raw biomass. So this is our combustion characteristics, where we try to find out the amount of fixed carbon, volatile content, moisture, and ash percentage present in our sample. As you can see, if we burn a sample from 0 degree to up to 1000 degrees Celsius, you can see the mass decreases for any sample. So this is a hydrochar sample where with the increase of temperature, so this is a hydrochar sample where if we increase the temperature, the loss increases. That means we are losing some content of our biomass or hydrochar. in this zone, we usually lose our moisture content, and after that, there is a big drop in the mass, which suggests that we are losing our content, and this refers to the volatile matter. And after that, there is not a significant change in the mass loss, which shows us that the remaining content is mainly the fixed carbon and ash percentage. And we can also see the maximum loss during this temperature zone. For example, here for this sample, we can see maximum mass loss occurs at around 300 degrees Celsius. This tells us that how a sample burns with the increase of temperature and what is the maximum percentage of mass loss can we get in this temperature zone with the combustion characteristics and DTG curve. So when we have a hydrochar sample or biomass sample, we can make pellets. Or why do we need to make pellets? Because we can densify our energy in a very small area. So as you can see, this is a pellet type structure. This is a pellet which looks like a cylindrical type structure, and we can find out the diameter. We can find our mass density and energy density. If we convert, on your right-hand side of the screen, you can see the graph where we can see if we convert our biomass to hydrochar, we can get higher mass density and energy density as well. So therefore, this suggests us that if we have our hydrochar sample made from our biomass after hydrothermal carbonization reaction, we can get higher densified material as hydrochar. So this is our Van Kraepelin diagram. We can plot this Van Kraepelin diagram if we know the carbon, hydrogen, nitrogen, sulfur, and oxygen content of our material. If you plot atomic hydrogen to carbon ratio and atomic oxygen to carbon ratio in the x-axis, we can see that there are multiple data points scattered in the graph. This Van Kraepelin diagram shows us that if the data point is close to the origin, that means it is a better fuel. As you can see here, anthracite is a very good fuel, and then the coal, lignite, peat, and biomass. But when we do the hydrothermal carbonization reaction, we can see the HTC char data points goes close to the coal, which suggests us that we are making a better fuel compared to the biomass if we do the hydrothermal carbonization of our sample. Finally, our conclusion is water is a magic solvent and transforms our waste biomass into valuable product. HTC enhances our energy content, energy yield, energy density relative to their raw biomass. While hydrolysis reaction is more prominent for low temperature HTC, dehydration reaction plays role for high temperature HTC. Hydrochar is an excellent energy resource with versatile other applications such as absorbent, carbon quantum dots, etc. Hydrochar is hydrophobic and resists moisture-induced damage. Pelletization eases the logistics and transportation problems. Finally, I'd like to thank our funding agency, USDA and USAID, and Idaho National Laboratory collaborators, and Florida Institute of Technology graduate student and undergraduate student of the Biofuel Laboratory. Thank you.
Thank you, Mr. Tahamid Islam, for your valuable lecture. I'm sure we are all amazed by the hydrothermal carbonization technology because that essentially what we're doing is speeding up the coal forming process that happens over thousands of years. We are actually doing it in a few minutes. And I think the main objective is to now optimize the process by understanding its kinetics and everything else using mathematical models and make a good process, make an economical process, because no matter how valuable the material is, if you don't have a very good process in producing it, it won't be very useful. So having that sorted out, we would move on to the portion where we are going to discuss about your adventure in your research life. So both of you were undergraduate students in the Department of Chemical Engineering, BUET, and also completed your PhD from Florida Institute of Technology. So what we're interested in knowing is how did your undergraduate studies help in this adventurous experience? So you probably solved a lot of different problems during your PhD. So how can we relate to those problems using our knowledge from undergraduate? So I would first ask Dr. Nipu Shah to start, and definitely Mr. Tahmid Islam to add in his opinions. I think you're muted. Yeah, we can hear you now.
Yeah, Shipyo, it's a long journey for me. I graduated in 2011 from BUET. So after my graduation, actually, I joined in a fertilizer company and I worked there for 3 years. So the time I studied in BUET, like we had very limited, even I can say almost zero opportunity to do research. You guys are lucky. So you guys have a lot of options to do research. So I don't say like zero because there are a couple of professors there are doing research, but as I said, compared to now, it's kind of zero. After working few years in industry, when I moved back to higher studies, it was very difficult for me to like cope up with the research because I didn't do any research in my undergraduate unless although we have like the thesis and the design courses, but that is very minimal. So when I moved into higher studies, one of the biggest challenges was to how I will cope up with the research. So if someone has no experience on the research, then he or she needs to spend few months at the beginning to cope up with that thing. So I was lucky. I had a very good supervisor in my master's. Although my research wasn't like related to clean energy, my research was process safety. So one of the example I want to say like how I correlate my work with the undergraduate study. So my research was like to design the vent for a reactor. Like if you have a reactor or a storage a vessel where always like vapor or gas is generating, that means you are pressurizing your system, so you have to release it. You guys know about the pressure release system. So my work was to solve like how can we design that system very effectively, because when people do that design in a like when you do the experiment in your laboratory, you use a small scale. So when you are taking a small sample in a small container, so your container to a vessel is kind of like in terms of mass, they are kind of same. So if you introduce heat, it will take like your sample and vessel both. So it will be like your vessel will take considerable amount of energy. So in that case, the amount of energy your actual sample will take is like, you have to consider your vessel part as well. So that was the design for like, they assume like, okay, all of the energy is taking your sample. So in that case, they design like a big vent. Sometimes that vent is bigger than the vessel, so which is kind of like not feasible. So in my work, I try to like correlate, like I went back to that heat transfer and I saw like, okay, how the vessel will actually take the energy, how much energy the vessel will take and how much energy is for the sample. Then I did that calculation like manually first to see like what I'm getting. Then when I convert that into the actual experiment, I saw, yes, that's the case we are getting. So my thing was like, I had that heat transfer in my mind. So I used that option in the research and find out the solution. So when I move into the PhD, one of the things, I think Tofik is here. So one of our project was to use that human waste to make the fertilizer. So one of my colleagues actually did those experiments and got the good results. And one day Tofik came and said, okay, can we make the economic assessment of this process and see like how economically viable it is? So up until that point, I had no experience on doing the techno-economic analysis of the HTC process. So I talked with my colleagues like who did the TA, and I read few papers. And when I talked with my colleague, when he talked about the sizing and economics, I went back to my design class as well as the, we had one chemical industrial management something course. That in that course we did the economics of the process. So when my colleagues talked about this process, I was able to connect those into my undergraduate studies. So one of the suggestions to undergraduate student, as this seminar is for the undergraduate student, when you read something, try to understand, don't memorize, don't read it for the exam. Just try to understand what you're reading, how we can utilize this. That will help you later on. Even if you feel like, okay, why I'm reading this one, it's not important at this moment, that's fine. But today or tomorrow, it will help you. So that's my journey, actually.
Absolutely. I would absolutely agree with the fact that the heat transfer and techno-economic analysis, these are very important things. These are fundamental things. And when you try to analyze a system, you go back to that in any way. And if you read advanced papers that deals with the transport phenomena, you're going to see it's basically the fundamental things that are helping you.
Exactly.
So I think Mr. Tahamid Islam also has faced similar problems. And would you like to recall some of your undergraduate experience and how that helped in your solving your problem?
Okay, thank you, Shupriyo. So when I moved into my graduate program, the research here is completely different from what I have done in my undergraduate thesis. So when I recall my undergraduate research experience, it is, if I tell it in summary, this is not exactly helping me in my undergraduate study, because I did not get that much scope to do research, because our theoretical course pressure is so high that we hardly had any time to focus on our research. And in terms of the facilities as well, yes, definitely. I wish if we had, when I got into my graduate program, the facilities here are very recommendable compared to what we have seen in our school, undergraduate. So the thing is, in terms of the research facilities, it might not be comparable, but definitely I would recommend that if in our undergraduate life, we do not have the habit of reading too much. For example, the research papers. So when we read a paper, we hardly can interpret the scientific description, or we hardly can find out what novelty is there in the research paper. So in that case, I think what I have faced is that during my undergrad, our memorization power is pretty good. So that helped us a lot in some aspects. For example, facing the term final or appearing the exam, or with the memorization power, we could overcome some part of that life. But here in graduate study, the memorization without understanding doesn't help you a lot, doesn't help you a bit, actually. So I think instead of memorizing any kind of topic, like for example, if you talk about heat transfer, if you talk about mass transfer, thermodynamics, there is a lot to do, a lot to understand, I should say. I face the same problem here. For example, thermodynamics 1 or thermodynamics 2, whichever you say, in my life, I know I memorized some part of it and just appeared the exam. But the thing is, we should understand it. Right now, I'm working on hydrothermal carbonization, and I deal with high pressure, high temperature reactor. Yeah. And now I can feel that mass transfer, heat transfer, thermodynamics, everything plays role in your career. Everything plays role in your career. If you do not understand those topics well, if you do not understand them well, then you would definitely face problem at some part of your life. And yes, and I should say, like, when I got into my graduate study, I met with my supervisor, Dr. Tawfiq Reza, and I learned a lot from him. I should definitely say that I learned a lot from him, like from theoretical knowledge to practical knowledge, how I should think in this way to solve this problem, and how I should proceed, how I should plan ahead before doing something, and how I should analyze experimental results. Yes, I must say I am still learning, and I have learned a lot in my 2 years of research, and definitely your undergraduate study will definitely help you. You get to know like where to find what, and then in this study, in this life, you have to really understand the thing, and you have to apply it in your actual experimental work.
So that sums up neatly about that topics we're learning in our undergraduate is actually very relevant when it comes to research, because when you talk about kinetics and thermodynamics, these are absolutely essential if you want to design a process. You have to start from the kinetics, you have to design the reactor, and then you go to the process. You can't just jump into the process at the same time. And if you want to have a good grasp on kinetics, you need to understand ODE. So let's not forget that we do also
let's
mathematics.
Not forget the mathematics part as well. So I think it is a snapshot what your undergraduate gives you. So you need to use it to further advance in your career. That's what I have learned so far.
And I think during your undergraduate experience, you don't get that much time to go back and learn it all, because you're already packed with a lot of experimentations. You have deadlines coming in one after another. So it's absolutely better because during the undergraduate time, the time you get, although we all know, we all have been through BUET chemical engineering department, and we know the stress. And I think every other department in other universities are also very stressful because there's a lot to study. But if we just study for the exams, it will help us a lot. So it's good to get that down again. Anyway, so contrary to both of your experiences, in recent times, the Department of Chemical Engineering, BUET, has had a paradigm shift, if I may, because undergraduate research is now becoming a trend among the undergrads. And I think there are a lot of undergrads present here. So you can say if you agree or not. So a lot of people are attracted to undergraduate research, but the thing is they don't have an idea what it's about. So what would your advice be to these people? What should they look for before joining a research group about or starting research or something? And what should be their focus? Is it just getting some results and making a publication? Is it just that, or understanding something? Even if you don't have any documented results, it's better to do the trial and errors and like learn something from it. So I would like both of your opinions on this, and I think it's very relevant for our undergraduates and for every undergraduates from a lot of other universities. So please.
David, you are gonna first, or I can do. I can go. Okay. So most important thing is your interest. So if you don't have interest on clean energy, don't do that like by watching this video. Like, okay, if I'm attending this seminar, I will go for clean energy. Don't do that. If you don't have an interest, don't do that. If you take a course, it's a matter of exam. So you take the exam, pass it, done. But if you go for research, like especially like the postgrad, like PhD, if you go for PhD for a topic you don't like it, you cannot survive. Because the research you will do in PhD, that's your life. You have to like carry that research like throughout your life. So first and most important thing, if you don't like, don't go. So you have to grow your interest on the topic first. So as soon as you grow the interest, then you have to dig into like, as an undergraduate student, I would say like if you plan for a postgraduate or a graduate program, then you have to think about like how to do research. Like first few things, like as uh, Shukriya mentioned, like do research, make publication. That is not very important. Like publication is, yes, it is kind of outcome, but if you go for publication, like not understanding the topic, not get the interest, then you cannot survive. So first thing is like get the interest, then like get into that topic, like what is the current status of that research. So try to see the current world and think about the future. So you have to plan like how you will go forward. So at the beginning, don't go for go for publication. Try to understand. Take time. So if you spend a year and don't publish anything, and if you see, okay, your colleague is publishing like 3 or 4 paper, don't desert it. Like you are building yourself. That is very important at the beginning of anything. Like for any job or anything, first few months, couple of years is the building time. You have to build yourself. If you do rush at this moment, at that moment, you will lose. At the end, you will be the loser. So for undergraduate, my suggestion will be like in the course, like whenever you are reading something, try to understand, don't memorize that much. In the research, like try to correlate your undergraduate study with the research. How can you, like when you're reading a paper, try to correlate, okay, why they said that, what could happen, like try to correlate like with your study. Every like in the research article, like I don't say 100% are right, some of them are wrong, like very few, because but when you will try to correlate like any each sentence with your undergraduate studies, you can correlate. If you cannot correlate, that means you have some lackages or that article is wrong. Don't say, okay, always article is right, I'm wrong. Don't say that. Try to correlate. Try to say, like, go one by one, match with everything. If you don't understand, ask your like colleague or someone, but like don't let it go without understanding. So that will be my suggestion to undergraduate.
So if Tahamid Islam has to add to it more, so please go on.
Yes, thank you, Shukriya. My suggestion to the undergrad will be, so if I compare my BUET life with the current students now, I would say in BUET, we had to focus on the theoretical courses too much, and therefore we hardly could get any time for like other research work, as I've already mentioned. But the thing is, what is in your hand is that you could probably develop your reading skill, writing skill, and communication skill. So in terms of the research, I would say if you, for example, from undergraduate research, I don't think professors in United States or any other country really expect that much that you will have high quality throughput or you will have high quality research papers or something like that. But as long as you develop or you build up your understanding towards the fundamental knowledge of chemical engineering, and it will, so when you will try to apply for graduate studies or whatever you do in your life later, it will definitely help you to, or it will definitely flourish in your work or in your understanding of chemical engineering fundamentals. And in terms of the research, I would say when you start your graduate study, if I compare myself with another researcher, so I would say like I am trying to develop my understanding and skill towards my research, whatever I'm doing. And at the very beginning of your research, like Nipu mentioned, that in the first 1 or 2 year, you will definitely not have that much of outcome, but don't be disheartened by that, because at the very like in the first 1 or 2 years, you are actually growing yourself from inside, and both from inside and outside, and you are trying to understanding the real life problem and trying to resolve or trying to make a novelty out of it. And definitely like if you do not have that much of a research experience or research understanding in your undergrad, you can definitely have scope in your life to grow up yourself in your graduate study. And I think, yes, as Nipu said already, that don't just jump into any topic if you like. Just try to understand the topic first, try to understand the research first, and then decide whether you are a good fit for the research or you want to excel in that research. And then only out of spontaneity, you can definitely shine in your research career.
So the key ideas from both of you is basically not to get carried away by the trend of doing something, but actually putting in some time and talking to your professors about what's it about and what kind of skills it you will have by being engaging with those research. And definitely for those who are already engaged in research, not to get disheartened by lack of results or any documentations, because that experience, if you can properly communicate that experience, I think it's going to be worth it. So
yeah. Shupya, you want to add one thing? Yeah, as already mentioned, you know, as an undergraduate researcher, like as Tahmid also mentioned, like when you will go for graduate, professor is not going to expect like 5 publications from you. Only thing will add value, like value to your profile, like if you have some experience on research. Doesn't matter like you publish couple of or not. So if you have some experience on research, that means like the problem I faced in my graduate study, like when I moved from industry, like I had to spend like 3-4 months just to understand like what is research, how to do the research. Even like when I changed my topic, like when I moved into process safety to clean energy, I had to spend like few months like to understand like what is the process. Like if as an undergraduate student, if you can just grow, like if you get the experience on that part only, like to how to do the research, what I need to look for the research, how we'll move forward. If you have that experience, that will add a significant value. Like that will like save at least 6 months in your graduate life. So that is very important, just to realize how to conduct research, what is research, what step I will take first and what will be the next. So that is very important.
Yes, I would like to add something more. The thing is, in what I have faced is that in your graduate life, you have to be very much organized and strategic. Like if you just without knowing something and you just get into experiments and trying to do something without knowing that like you should go, you should approach in this way or in this way. So I think and this is a very crucial decision for this is about decision making. So for example, we study I think management in 4th year, last year of undergraduate.
In our last semester.
Yeah, in our last management, right? So they talk about it teaches us how to make decision, how to plan ahead. You worked on activity diagram or whatever it was. So activity diagram or experimental plan or decision making, managing people. So I think this plays role in your graduate life as well. So you have to be strategic. You have to have your own work plan, and you have to decide like which way you should go at the very beginning, or at the very crude moment of your research.
Okay, that's absolutely correct. And I can see Dr. Tawfiq Reza has raised his hand. Please, Dr. Tawfiq Reza, I request you to share your opinions.
Well, thank you, Supriyo. I just wanted to add something. I mean, Niput, I mean, you're doing a wonderful job, and I think that the point are almost, I think all of them are actually covered there. I just wanted to say something to the undergraduate students. So this is something that I always tell to my undergraduate student that I teach here. So they would come here and they would say, when do I start? Okay, I mean, should I do research in my 4th year? Should I do my research in 3rd year? Should I do research in 2nd year or 1st year? So if undergraduate students start as early as possible. Okay, so there's nothing written that you have to do it in 4th year or 3rd year. So if you're interested, you talk to your professors and then come up with that, and then start coming to the lab, going into that environment. The second confusion that we have is that from the undergraduate student, like, I don't know any topic. How do I know which one I don't know? This is something that probably you have your own interest, or probably when we talk at this class, we would usually introduce our research a little bit, talk about more about the current problems that we are facing. And some of the problems you would actually pick it up, and then you could start discussing with your professors, and then say like, hey, I'm interested to learn more about it. So there's nothing wrong with that. So that the professor-student relationship is supposed to be very friendly and very transparent as well. So if you can get more information about what they're thinking, they're not here to just give you a grade. They're here to develop you. So just think in that way. The third question that I usually get from the student is, I'm not interested on PhD. Do I still need to do research? Yes. If what it would do is, I mean, eventually when you graduate from BUET, or when you graduate, all you have is your GPA. It doesn't tell you everything. So you need to stand out from the others. So how do you stand out from the others? I mean, of course, GPA matters. I should not say it doesn't matter, but if you could if you could develop other skills, for example, if you know how to run experiment, if you have a technical skill, if you have a writing skill, communication skill, this would actually add a lot of value to your proposition. So you do not absolutely have to go to grad school to actually do research. Research is for your own career development. You can take it to your industry. You can take it to anywhere you would want to go. And the last thing I want to add is, this is what I tell my undergraduate student, like, you need to enjoy yourself. So this is nothing that I come here, I do 5 hours of work, I have absolutely no interest. So this is something you really need to enjoy. So as soon as you stop enjoying, please talk to your peer or talk to your professor, and then say like, yeah, you know what, I'm not really enjoying it. So maybe you don't understand it, or maybe you're just not into it. Like for my personal thing, I have very high admiration for the biomedical research, but I don't know anything about it. And if they can talk like whole day, I would only say like, okay, it's going over my head. So that kind of thing. I mean, if you're really into biomedical research, you would actually go into that. And it is not a bad idea to what we call the hopping around the laboratories, right? So you talk to your professor, work with that professor for a semester. If you're enjoying it, carry on. If you're not enjoying it, move on. Okay, so I guess Konish wants to add something else. I'm going to stop over here. Sorry to take your time.
So definitely, we are excited to have Dr. Kitania with us. Please, Dr. Kitania, we would like your opinion on this as well.
Thanks, Shubhrio. Actually, Tawfiq covered a lot of things, and I have to just add just one sentence that already Nepu said, and Tamit said that they didn't experience much of research during their time in BUET. So actually that has definitely changed now, and they have a lot of options now if they want to work, and if they want to get some experience. I think there are actually 4 to 5 active research groups now. So they're having all sort of like postgraduate, undergraduate students, all of them are joining different groups according to their taste. So I think this is the case for Bangladesh Agricultural University and also University of Dhaka. So they are also doing that. I think research is getting traction in these universities now with the new faculty members, in the sense that not new, younger faculty members who are coming back and joining and then contributing. So not taking any more of your time, Supriya, please go on. I think Nepu and Tamid might have some questions from the audience. I'll just stop here. Thank you.
Okay. So we definitely had a very rich conversation about undergraduate research and how it can help our careers in the future for research. And we are very glad that Dr. Kitania and Dr. Tawfiq Reza has joined us to share their valuable opinions. It's always fun to have them chime in. And so I think we have had quite a long discussion session, and we would like to move on to the question answer session now. So I would like to hand over to Samira for the question and answer sessions. And thank you for your time with me. So thanks.
Thank you, Supriya, and all our discussants and speakers for this very enlightening event. So I would like to ask the participants, if you have any questions, you can put it in the chat box, or you can also raise your hand and say it loud. If anyone has any questions. So I believe we had a very long discussion and speaking session. So people probably already got their answers, what they wanted to ask. So we have now reached the end of our session, actually. And I would like to thank everyone, all the participants, our speaker, Dr. Nepu Saha, and also Reza sir and Cornish Kitonia sir for adding their insights. I'd like to briefly introduce you to our organizers for this event. So this event would not have been possible without the organizers of this event. All of us are from the ECR group, and we have also had a very rich cooperation from all the other ReHyCaRe partners, Bangladesh Agricultural University and University of Dhaka, as well as Florida Institute of Technology. So I thank all of the participants for patiently waiting and hearing our talk, and I apologize for the slight inconvenience we had. So now that we have reached the end, I would like to ask everyone to stay tuned for our next event. We're actually coming back very soon with new exciting events, and we will try to accommodate the sessions focusing on clean energy, as well as directing a lot of it towards the career aspects and research highlights for the undergrads. Thank you all. So I think we can now end this session, and I thank everyone again for joining us. Thank you.
Thank you so much. Thank you for thank you organizer for inviting me, as well as the audience who attended this discussion and the presentation. Thank you for your time.
Thank you so much for inviting me as well.